for the presentation. Now welcome Pranab Prakash Mishra to present his topic. Now I will be talking about lock-in detector. Now we will be discussing about lock-in detector. So we know about normal detector. So now what is the difference between a normal detector and a lock-in detector? Normal detector, they detect signals which are which we can distinguish from the normal noise components in the environments which are naturally occurring. But in the when the noise are very small, I mean the signal is very small in size, in the order of nanovolts, compared to the noise which is in terms of volts or higher. So in that case, we use lock-in detector to extract that signal from the noise component. Now, what is locking? So this term we need to know. Locking is a term. Literary meaning is little bit different from the meaning what we do in the detection process in the technology. Literal meaning is to identify something which is very small or minuscule, which is hard to identify. So let's say there are a flock of swans are flying, and within them is a crane. So they all are having white in color, but we can't distinguish the crane from that flock of white swans always by looking at it. So we need to lock onto it, so that for locking onto it, we first have to have the information part. Does a crane look like? Let's say we can be locking it onto it by naked eye. So we would be using some instruments like that has programs to lock it onto it. So that is like a old example. We can say it more better in terms of fighter jets. Many fighter jets are there. Then when they are flying in formations, then we need to lock into one fighter jet. For that reason, we use locking in radar systems, and that by locking that thing is analogous to locking. Now let's go the context lock-in detection. Why do we use the lock-in? Now uses of lock-in detection, and these are the contexts. Lock-in detection, as I said, we use it to measure very small AC signals which are in the order of nanovolts from the noise pattern that is in higher order. And how do they use the process? They use the phase detection technique, phase sensitive detection technique, to single out the signal component that is mixed in the heavily noisy environment component. So noise signals, the other noise signals, the noise component is treated as noise signal. They are discarded, and only the signal component is extracted from the noise in the environment. Now, let's move to why use the locking. Now, why do we use locking and instead of a normal detector? Amplifiers and bandpass filters, they can amplify large signals. I mean, these are very small signals which has the signal of our interest as well as the noise. So interest signal is very small, but noise components are very high. From this a nanovolt, with just little bit might be the signal of interest. So we can't get that signal by using oscilloscope or other amplifiers and bandpass filters, and then we can after amplification and filtering, then also we can use oscilloscope to extract that. Then acquisition times becomes very high. We need, let's say, an environment in which it is fast changing, But let's say there is a door. We have a door. Then the door is automatic. It sorts whenever no person is there. It sorts automatically. But when let's say I am walking to the door, and at that time a cat enters, but the door doesn't recognize the cat. The cat would be entering very at speed, and at that time if the door sorts, then the cat would die. So for that we need to know that the frequency of the cat, as well as we will be using a photo detector for taking the to know the position of the cat. So if the the door can't identify the cat because there are outside lights that there are other normal sunlight is there, so photo detector has to be sensitive. For that time we need lock-in detector. So the cat would be going at very high speed. So for that we need very low acquisition time. It senses immediately and doesn't close the door. So that's why lock-in detector is useful. Now signal is too weak, as I told. Signal to, it's not visible, small signal to noise ratio, if it is there. I mean that the signal to noise ratio means that the noise, the component of signal in or within the noise. Now, uses of lock-in detector. Before moving on to the principle, we should be knowing its uses in physics specifically. In engineering, they call it as lock-in amplifier, but in physics, we use it as detection purposes. For detection purposes, so we call it as lock-in detector. So we use it for sensitive AC voltmeter. I mean, the voltage is when it's in the order of nanovolts, then we can use it, the lock-in detector, to detect those voltages. And we use it in scanning probe, microscopy, atomic spectrum analyzer. Whenever we throw light into atom, I mean pass light and other things into the atom, electrons, then the spectrum are having very low signals in comparison to the noise that, I mean, that unrequired signals which are offered, which are transmitted from the other atoms. For that we need lock-in amplifier or detector to extract those. Now imaging of bond characteristics between atoms of the molecule, for that also we use lock-in detector. Now let's uses of process of lock-in detection. So first I will be explaining a process. Let's say that's the sample. Laser, we use the laser, we throw laser to the sample, we pass the laser, and now we use this chopper control. Chopper is a device that is used to create a signal of our interest, or I mean to create the reference signal as well as modulate the signal of the laser to have the information about it. So when we use the chopper control, then reference signal is created, we get the reference signal as well as those laser is chopped and that is applied to the sample, and fluorescence of the sample is taken and it is detected, and in the lock-in amplifier we match the reference signal with the signal coming from the noise, embedded signal coming from the sample, and single out our signal component, and then we take the output and amplify it and get the result. Now, principle of lock-in detection, it combines the techniques of time and frequency analysis in the different domains. For that we use Fourier transforms. And how do we do that? Now, for doing to get the specific signal, we multiply the signal with our reference signal. I mean that let's, as I told about the cat, so we will be taking the signal of the cat, the signal created by the movement of the cat, along with the signal of the noise that is in the environment. So whenever the cat is moving, specific signal of the cat and that of the cat moving in the noisy environment signal, and whenever we multiply those both signals, then two components are formed. So those components are separated out. One gets the AC component and one gets converted into DC component. That happens. So we will moving into yes, one sum and difference. That will be. So this part is one component, another component. We multiply it, multiplication, and then through 1/2 cos formula, that sin v formula, we get this component. This is the higher component, which is the frequency gets added, and then it is removed by the low pass filter, as you can see here, and then a component is gets subtracted, the frequencies are subtracted, then it results in a lower component. So it is kept here, and it is generally a DC component, and it is a AC component. So and we have to put the band pass filter bandwidth as required. I will see it in the rest. Next slide. Yes. So this thing here, the phases of the locking signal is taken into consideration for filtering. So we call it as phase sensitive frequencies. Now phase sensitivity of the locking amplifier. When we take two signals and multiply it, then we get two phases. When the frequencies, when the frequency is added, this part is taken out. This is filtered out as it is the AC component. The remaining part is this one. So when this omega 1 is equals to the omega 2, then we get two cases here. So for phi is equal to 180 degree, and phi is equal to yes, phi is equal to 0 degree, and phi is equal to 180 degree. So we will be taking these equations in terms of voltages. I mean that volt electronic signals. So when this electronic signal is 1, then we will be in phi is 0 or 180 0, then we will be getting the electronic voltage as 1. And when it is 180 degree, it is out of phase, then we will be getting negative electric volt. And when it is phase difference, and whenever it is plus or minus 90 degrees, it gets attenuated. Now locking analysis, we can use the other signals for locking analysis too. Let's say the square wave or the other square wave or sawtooth wave. Those can be transformed into the normal sine and cosine terms to Fourier transform. Why do we use using Fourier transform for transformation? Because it is easier to transform, easier to measure the sinusoidal and cosine signals rather than the sawtooth and other types of signals. Now low pass filter and bandwidth. So as I said, hereby this is the low pass filter. Here the bandwidth is this much, minus 3 dB. So when the low pass filter is taken high, so I am talking about bandwidth and filter order and their characteristics, how it affects the noise to signal extraction process. So whenever the low pass filter is taken very small, then what happens? Now the bandwidth is inversely proportional to time constant. So whenever the bandwidth is small, then the acquisition time becomes low, but we fast. Yes, when the bandwidth is low, measurement will become low, but when the bandwidth is large, then the measurement will become fast. Because thereby the cycles are, we take sum of cycles and then average it out for taking our signal, and because it is embedded in the noise, so we do averaging here by to take. So whenever we make the bandwidth large, but some of the AC components hereby, when the bandwidth is large, this AC component, as we are saying, this leakages into the DC component. So we don't get the real signal, but though we get a faster measurement, but we don't get the real signal. And whenever the bandwidth is made narrow, then the noise will be significantly cut off. We will get real signal, but the acquisition time will become high. So measurement becomes slow. Time constant and Q factor, as I said, the time constant is the time over which we average out the signal. Hereby, this shaded part is about the averaging process. If we average it totally, then it becomes 0. But if you average it up to this much, then we get a positive signal, but that wouldn't be the right result. So we need to average it over a long time to get the right result. Now the Q factor, quality factor, is defined as the quality by the capability of the amplifier to extract the noise, the order. So that is given by frequency with the change of frequency. The longer the time constant, it gives the better Q value. The higher time for which we average the signal, then we get better quality of the signal to noise ratio. But thereby the acquisition time becomes high, and we get slower response. Commercial looking have about Q of 100, this 1 lakh. Now the some parameters for having a good locking detector. For a good locking detector, the frequency range and maximum measurement bandwidth should match the application requirements. We should set the bandwidth and the frequency range as according to our requirements, and it will be varying over time. So the better we match it, the better results we get. It should have a good dynamic reserve, as we said that there is a dynamic reserve present in the locking amplifier. So this one, when set appropriately, we have the AC component is weeded out. So that is what it is used for, and gives accurate results. The integration of multiple instruments. If a locking amplifier is having too many connections, then we can integrate more number of instruments like oscilloscope, detector, numerical plotter, and all. So information of time and frequency domain can be integrated onto it to get the signal. A noise component is not only in the, we can analyze it better in only in time domain or in frequency domain. We would be requiring other domains to analyze it. So for that, we need multiple instruments, and that should be, we should be able to connect them to the amplifier. And the conclusion, the signal is logged from an LC environment. After we take it, it is fed to the amplifier and amplified. There are two types of locking amplifier, and one is analog, another one is digital. A is missing. They detect movement square signal of the operating frequency. The digital locking amplifiers apply algorithms and have increased the signal detection efficiency by multiple. There are different types of signals like the continuous signals and the time varying signals. So these are used in digital amplifiers. We use the data created through softwares to extract the signal from the noise environment. And these are the references.